So in this topic, you're going to be studying sections of 2 chapters from the book, all of them related to fluids. The first chapter, chapter 11, is all about general properties of fluids, so just looking at the basics of them, densities, pressures, things like that. The second chapter, chapter 12, is going to go into either fluids moving or things moving through fluids, so experiencing things like drag. So, basics of the first chapter. Firstly, what this is doing is applying an awful lot of the stuff that you really already know and have already studied, or a level of logic that you've already applied. So, for example, things like density being mass over volume, pressure being force over area, all of those things still apply. It moves on a little bit in section 4 to looking at a few equations which are then specific to fluids themselves. Now, this is pressure at depth. Now, just to make one little point, and it does say this in the summary there, that liquids and gases are both classed as fluids. So fluids are things that can flow. Liquids and gases both do that. So all these things apply to both of those. But we do make some assumptions, usually in that things are incompressible at times, especially when you get onto the second part and you're looking at rates of fluid flow. Obviously, when things become compressible like air is, then you have to start bringing gas laws into it, which is where we will get to a little bit later on. So the first application of something specifically fluid related is this pressure at depth equation here. So the pressure at depth is the depth under the water, so H is depth. It's height of fluid above that point. The density and gravity. It's also worth noting that, of course, if you apply a pressure at any point through a liquid or any fluid, that pressure is applied all the way through that liquid. In addition, it will then also have the pressure due to the depth. So if you just go back to my little scribble of a beaker up here, if we've got an initial pressure applied to the surface of this, and we want to know what the pressure is under the surface here, then there's going to be the initial pressure rho naught, P naught, but there's also going to be the pressure due to the height of the liquid. Basically, the weight of the liquid pressing down creates that pressure. So it's an interesting model to get into, but there's also a little bit more information in this on the extra videos that you put up, which involves deriving these equations and looking at the ideas of where these come from, which is a very good way of looking at the basics behind a model, especially when you get onto this section down here. So Archimedes' principle. Archimedes' principle is just the idea that if you've got an object, and it doesn't have to float, okay, it can be a thing that's sunk to the bottom of a tank or a lake or whatever, but that thing which is submerged in a fluid, remember that doesn't have to be water, has displaced, there we go, an equivalent amount of that fluid of its own volume. Or maybe if it's floating on the surface of water, it'll be less than its own volume. But it experiences an upthrust. And the upthrust is equal to the weight of the displaced fluid. Now, it's important to note that is not equal to the weight of the object. If it's floating, then it is. Okay? So this is a really interesting principle to get into and kind of think about and play with a little bit and practice some questions on it, because it really starts to get into your physics way of thinking about things. But what's even more important is you have a little look at where this model comes from. So again, in the video that derives the equation up here for pressure at depth, that then links to the Archimedes principle, and the pressure at depth equation derives, or is the basis of the derivation of the Archimedes principle itself. The section finishes with a little bit on mainly capillary action, I think, is the thing you want to concentrate on at that section. Up to there is most important, but have a little look at the capillary action stuff because you will need some of that. The pressure in the body is a nice little application of some of this stuff, but it's not something we specifically want to study. So it's there as extra reading if you want to, if you've got time to go to it. Moving on to the second section, which is chapter 12, now we start to look at fluids that move. So we're looking at things like flow rates. So, for example, just to give you an idea of what we're thinking about, if you've got a tube and you're putting a certain volume of water into that every second, that's a flow rate. But if that tube narrows, that fluid still has to go somewhere. So the same volume per second is still coming out of this tube. But if you think about it, now it has to flow faster because the volume has been narrowed in terms of its cross-sectional area. So the length of that amount of water coming out in 1 second has to be a lot longer. So let's say if the amount of water fitting into that tube is, that big, the amount of water coming out of that tube in the second is going to have to be that big. And that has to happen in 1 second, so the velocity would have to increase. And it would be, in ratio with the change of area. So it's really applying just basic geometric logic, which you are already starting to develop, but applying it now to situations where things are moving. So you're building a little bit on that kind of 3D imaging part of your brain. The Bernoulli equation is nice because it actually serves a lovely different purpose. This looks like horror, but it's not. Look at every part of the equation. So if you find you're getting into the habit of looking at something complicated and going, oh, I can't understand that, this is going to really help you to learn to break things down a little bit. So look at each part of the equation, all right? What do each of these terms actually mean? And what does the thing do as a whole? And how can you use it? And you can only really do that if you've got a basic understanding of what it does, and then have a look at some of the examples. And again, in section 12.3, which is the last one that you've got to study, it just goes into some of the applications of and takes that Bernoulli equation a little bit further. So in this one, you're going to be looking at a few things along the lines of drag, so motion of a fluid and motion within fluids as well.